Okay, let's move on then. In the last class, we discussed the nomenclature of coordination compounds. Today, I would like to discuss another important feature of coordination compounds. It's coordination numbers and structures. So, first of all, what do we mean by a coordination number? So, a coordination number of a complex has is nothing else but the number of attachments or points of attachments between the ligands and the metal. So certainly the coordination number will influence the structure, but there may be different structures for a given coordination number also. So let us think about what can determine a coordination number, which can then determine the structure. So can you think about what properties of a metal or what property of a ligand could influence the coordination number? Anne? Yeah, for instance, the oxidation state, that's correct, the valency. That is also indirectly connected to another property, which is the size of the metal. So generally, when we have a higher positive charge of the metal becomes smaller, and that certainly can influence how many ligands we can fit around the metal. Okay, so the size of the metal ion is certainly one important parameter. What else could be important? Virtual students are also invited to answer either via chat, or you can also unmute yourself. We can actually hear you in the classroom. Okay, there's one answer in the chat. The d electrons of the metal. Yes, very good. So the electron configuration will also determine the coordination number. So when we look at the ligands, what properties could influence the coordination number when we consider the ligands? Pardon me? Can you repeat the question? What properties of a ligand could influence the coordination number?
What about the charge of the ligand, whether it's neutral or charged?
The type of bond that the ligand would make.
The type of bond?
Yeah, like if it was a beta bond or...
Yeah, that's correct. So certainly the type of bond, also whether it's a single bond or maybe a double bond. But I see another suggestion here in the chat. Yeah, the type of ligand, if it's monodentate, bidentate, when it has more possibilities to bind, then it can use these possibilities, and that would increase the coordination number. Correct. And then simply the bulkiness of the ligand. Okay. So if we have a very bulky ligand, then we can just fit less many around the coordination, around the transition metal. Okay, so last but not least, there is also the possibility that the solution state or the solid state has an influence on the coordination number, because in the solution state, the molecules are far apart and only interact with the solvent, while in the solid state, they are close packed, and that can also have an influence. So we have the shape and size of the ligand, the size of the metal ion, the electron configuration of the metal ion, and the intermolecular interaction solution versus solid state. So you see that this gives very many factors that can interplay, and for that reason, it's relatively difficult to predict the shape of complexes. However, there are a number of rules with which you can predict the coordination number and also the shape of a complex with fair accuracy. In the following, I would like to walk you step by step through all the possible coordination numbers and associated shapes, and under which conditions you most likely will observe them. All right, so let's start with the so-called low coordination numbers. And these are the coordination numbers 1, 2, and 3. So the lowest coordination number is obviously the coordination number 1. So generally spoken, would you expect that this is a common coordination number or an uncommon coordination number?
Uncommon.
Uncommon. Yeah. So you would think this is fairly uncommon because, well, an exposed metal site with only one ligand attached is likely reactive and likes to attract more ligands toward it. So indeed, the coordination number 1 is pretty uncommon, and typically you require a very bulky ligand in order to achieve a coordination number 1. There are some instances in which coordination compound appears to have a coordination number 1, but this is not really so. So an example is, for instance, methyl lithium. So you may imagine methyl lithium is a very simple molecule with a methyl group and a lithium atom in between them, and with a covalent, polar covalent bond in between the methyl group and the lithium. But this is actually not the case, okay? This is because that would result in a coordination number 1, which is just leading to instability. So in this case, what molecules like to do is cluster formation that increases the coordination number of the coordination number. So in the case of the methyl lithium, you're actually forming a tetrahedral cluster out of 4 lithium atoms, okay? And then above the faces of that tetrahedral clusters, you have the methyl groups. So you actually do not even have a traditional 2-electron, 2-center bond here. So this is one way to view the methyl lithium. You can also view it as a cubic structure in which 50% of the corners of the cube are occupied by the lithiums and the other 50% by the methyl groups. Okay, so this is actually shown here. So here you see a cube which is, well, somewhat distorted, and you see 50% of the corners are occupied by the lithium atoms and 50% of the corners are occupied by the methyl groups. You can see this also here in this schematic picture. You can actually inscribe a tetrahedron inside of a cube by occupying just 50% of the tetrahedron, 50% of the 50% of the corners of the cube, and then you occupy the other 50% of the corners inside of the cubes with the methyl groups, and then this gives overall a cubic structure. Okay, so the methyl groups are also oriented in a tetrahedral way relative to each other. So if you connected all the carbon atoms here, then that would also be tetrahedral. Okay, so now what is an example of a coordination compound where there's really a coordination number of 1? And as I said before, this is very rare because you have to wrap a very bulky ligand around metal so that this metal cannot make interactions to other ligands or even just solvent molecules. So an example is this thallium compound here with only 1 thallium atom bonded to a carbon atom via a polar covalent thallium carbon bond, and we see that this carbon atom is part of a very bulky ligand that wraps around the thallium tightly. And for that reason, the thallium cannot coordinate to other ligands or even just solvent molecules. Here's also just shown how you can make this compound. You can make this compound from the respective organolithium compound. But the lithium is so small so that also ether molecules can actually coordinate to the lithium. So again, in this case, the lithium does not really have a coordination number of 1. But when you react this organolithium compound with thallium chloride ether, then what will happen is that lithium chloride forms, so you actually have a metathesis reaction, and you will get lithium chloride, and the thallium binds to the carbon. The thallium actually exactly fits into the pocket provided by the ligand. Okay. Let us move now from the coordination number of 1 to the coordination number of 2. So similar to the coordination number of 1, this coordination number is rare. However, it's already significantly more common, in particular, to metals that have the 10 electron configurations. So metals with the 10 electron configuration tend to like the coordination number of 2. There's a fair number of examples for that. So what are examples for metal ions with the 10 electron configuration? So examples are, for instance, silver plus, copper plus, and gold plus. So imagine your periodic table in your head. So the copper, the silver, and the gold, they are in group 11 of the periodic table. That means that they have 11 valence electrons. Okay, so of them there are 10 d electrons and 1 s electron. Now you remove that 1 s electron and you have no electron left in the s subshell, and you have 10 electrons in the d subshell. So this makes these ions, the 10 ions. So similar for the mercury is in group 12 of the periodic table, has 12 valence electrons. If you remove the 2 s electrons, then the 10 d electrons are being left, and that also makes the mercury 2 plus d10 ion, and these ions actually like the coordination number 2. So I'm just giving you a few examples here. So some of them you have already encountered in the class. So this one here you have already encountered. So silver plus makes a complex with ammonia to make a diamine silver plus. And in this complex, really the silver has a coordination number of 2. So the 2 amine ligands, they coordinate the silver actually linearly, and you really have a linear complex. Similarly, you can replace the amine ligands by cyano-ligands. Okay, so again, you have silver in the oxidation state plus 1, that makes it a 10 ion, and the respective complex called the dicyan silver minus complex is linear and has the coordination number of 2 at this silver. So here's an example for copper complex CuCl2 minus. So we have here copper in the oxidation state plus 1. We have a copper 1 plus ion, which is coordinated by 2 chloroligands in a linear fashion. So here we have mercury cyanide. So that's also a linear complex, and here we have gold Cn2 minus. So again, gold is group 11 metal. So if you remove 1 electron, it becomes a d10 gold plus ion, and we can coordinate 2 cyano-ligands to that gold plus to make a linear complex of position gold Cn2 minus. Also, structures that are considered to be, well, ionic compounds like mercury oxide or mercury sulfate have the respective ion coordinate in a linear fashion. Can I just show you this? So here's the structure of mercury oxide, and it's actually a polymeric structure. And you see that the mercury is coordinated in a linear fashion by the oxide ions. Okay, so these chains are actually bent here where the oxygen is, and that's because of the electron lone pairs at the oxygen. Okay, but overall we have a linear polymeric structure for the mercury oxide. So here above you just see the actual structure for the diamine silver plus ion, where you can see that the silver plus ion is coordinated in a linear fashion by two amine ligands. Okay. So now how can we explain that these ions tend to like the coordination number 2 and that they like to make linear structures? And oversimplified explanation is that they have a D10 subshell which is full. So we not necessarily need to consider these 10d electrons as valence electrons anymore. Then only the empty s and p subshells are being left as basically valence orbitals into which the ligands can donate the electrons. And when we have two ligands which are two electron donors, then these two ligands tend to bend away as far as possible from each other. Okay, so no electron lone pairs that are sterically active if we consider the d electrons not to be valence electrons anymore. And this is a very crude explanation as to why these complexes like to be linear. Okay, so we can just assume an sp hybridization which leads to a linear shape. All right, so what about the coordination number? So when we go away from the D10 ions, then we only find examples very rarely, and only in the case we work with very bulky ligands. Okay, only that can again stabilize the coordination number of 2. Okay, so let's go from the coordination number 2 to the coordination number of 3. Also, the coordination number of 3 is relatively rare. Again, D10 ions are most commonly observed for this coordination number. So here is one example. So this is the tricyano copper 2-. What is the shape of this complex anion? It has a trigonal planar shape, and this shape is generally the most common shape for the coordination number 3. We can again, in oversimplified way, say we would expect such a trigonal planar shape when we have D10 ions. We just do not consider the D10 ions as valence electrons anymore, so only s and p orbitals are relevant. In this case, we would make an sp2 hybridization, which would explain our trigonal planar structure. So again, if you want to make other coordination compounds with the coordination number of 3, then we have to work with bulky ligands in order to stabilize that relatively low coordination number. Okay, so now let's go from these low coordination numbers to intermediate coordination numbers. And these are the coordination numbers 4, 5, and 6. And these are the most common coordination numbers. So why are they the most common? Because of statistical reasons, there are many metal ions around which that have appropriate size for 5 to 6 ligands. And well, there are also many ligands that are neither too small nor too big to result in a coordination number of 4 to 6. So the coordination number 4 is actually the second most coordination number after the coordination number 6. So the most common shape associated with the coordination number 4 is the tetrahedral shape. So when is the tetrahedral shape generally preferred over the octahedral shape? So this is typically the case when we have smaller and highly charged cations. So there are actually two examples here, the chromate and the permanganate. So the chromate has the chrome in the oxidation state +6. So we can imagine that a chromium +6 ion is a very small species, so it won't accept many ligands around. And even when the ligands themselves are not particularly big, like these oxoligands. And the same for the permanganate, with the manganese is the oxidation state +7. Also in that oxidation state, you have a very strong contraction of the respective ions, so that not all that many ligands around that ion are accepted. On the other hand, coordination number 4 is preferred over the coordination of 6 when the ligands tend to be bulky. So here's an example in which copper plus is coordinated by 4 relatively bulky pyridine ligands. There's also another argument that we can make why the copper plus prefers the coordination number 4 over the coordination number 6, which is that it's the 10 ions, so generally 10 and the 0 ions, they prefer, as you have already seen from the previous examples, relatively low coordination numbers. So they also prefer the coordination number, relatively low coordination number 4 over the coordination number 6. Okay, so we can think about, well, why is the tetrahedral shape the most common shape for the coordination number 4? And that's easy to answer. The answer is that, well, in this case, all the ligands have the greatest distance from each other. Okay? However, the tetrahedral shape is not the only shape for the coordination number 4. Can you imagine another shape?
Square planar. Square planar.
Sorry?
Square planar.
Oh yeah, square planar. Yeah, the transcriptions are actually good for something. It's astonishing what this microphone picks up actually from the distance. Okay, that's right. So square planar, that's actually the second most common shape. So when do we observe square planar structures? In particular, when we have D8 ions, and we will learn later in this course why D8 ions actually prefer square planar structures over tetrahedral structures. So let us think about what are common D8 ions. So for instance, D8 ions are the divalent ions of the group 10 metals. So nickel 2, palladium 2, and platinum 2. So here just a couple of examples. This is probably the most famous example. So this compound is called cisplatinum, which is known for its anti-cancer properties. It's also used as an anti-cancer drug, where we have the platinum coordinated to 2 chloro groups and 2 amine groups, and it's called cisplatinum because the amine groups and the chloro groups, they stand in cis orientation to each other. Okay? So they're an adjacent. position, so we can easily see that the platinum here is in the oxidation state +2. So the chloro ligands are anionic ligands, the amine ligands are neutral ligands, so the overall complex is neutral. So therefore the anionic charge or the negative charge at the chloro ligands here must be compensated by positive charge of the platinum. The platinum must have 2 positive charges so that the overall complex becomes neutral. All right. Here's just another example with nickel. So in this case, we have a tetra. So yeah, no. Nickelate 2 minus. So again, we can easily see that the nickel is in the oxidation state +2 by considering that all the cyanoligands are negatively charged. So we have 4 negative charges. The complex A9 has a 2 negative charge. So we need 2 positive charges in order to go from -4 to -2. So -4 + 2, that gives -2. Okay, now as we go away from group 10, can you think about other metal ions that are the 8 ions? So we can, for instance, go from group 10 to group 11. In group 11, we have copper, silver,
Copper 3.
and gold. So now, how many electrons do we remove? Do we need to remove from copper, silver, and gold so that we're getting a D8 ion?
3 electron. 3 electron.
3 electrons. Yeah, 11 minus 3, that gives 8.
That's copper 3.
Okay, so we need copper in the oxidation state +3, silver in the oxidation state +3, and gold in the oxidation state +3. And that's relatively rare for copper and silver, but it's actually fairly common for gold. So gold is what is fairly stable in the oxidation state +3. So here just a few examples. So AgF4- is an example. Okay, so we have here 4 fluoroligands which have a 1- charge each, so that gives 4 negative charges. So the complex has a 1 negative charge, therefore the silver must have the oxidation state +3. So here's another example, tetrachloroorate 3. So again, the 4 fluoroligands have a 1 negative charge each. That gives 4 negative charges overall. The A9 has a 1 negative charge, so -4 + 3, that gives -1. Okay. Now, last but not least, we can also go from group 9 to group 10. And then we are with the metals cobalt, rhodium, and iridium. So now, these elements have 1 electron less than the group 10 metals to begin with. They have only 9 electrons, so we only need to remove 1 to produce a D8 ion. So now copper is not, cobalt is not stable in the oxidation state +1, but rhodium and iridium are. There are fairly many examples of rhodium and iridium complexes in the oxidation state +1, and they are often square planar. So here's just, again, a few examples. So this is a fluoro-tris triphenylphosphine, according to our nomenclature rules. Rhodium 1. And why is the rhodium in the oxidation state +1? Well, these phosphine ligands here, they are all neutral. The chloro ligand is anionic. The overall complex is neutral, so therefore rhodium must have the oxidation state +1. So here's just one more example with iridium. So in this example, the iridium is bound to two triphenyl phosphine units, one chloro ligand and one carbonyl ligand. So the chloro ligand is again the only negatively charged ligand. That's a neutral molecule here, so the iridium must have the oxidation state +1, as we would expect, because the iridium is a D8 ion. The complex adopts the square planar shape. Okay. So when we go to other ions, but D8 ions, then we observe square planar structures only if the ligand imposes planarity. So an example for that is a porphyrin ligand. Remember? We discussed porphyrin ligand, the porphyrin ligand in the last class. So this is a tetrahedral ligand which has a ring structure, and the 4 nitrogen donor atoms lie within a square plane. Okay? And that whole cycle is rigid. So therefore, any metal that fits inside must adopt the square planar coordination. Okay, so here's another example. This is the a so-called Saline complex. So this ligand here is called a Saline ligand. So it has here this ethylenediamine unit connected to these 2 carbons here, which are then connected to these 2 benzene rings, and there are 2 oxo substituents here at these positions at the benzene rings. So again, the donor atoms actually lie within a square plane, and for that reason, we force the metal to adopt the square planar coordination. And like I previously said, here we have the porphyrin, where we have the same situation. So we have the 4 nitrogen donor atoms that make a square, and the metal is just being forced into that square. And for that reason, it's coordinated in a square fashion, even though it may actually prefer another shape. We would prefer the tetrahedral shape. Okay. Then the last possibility, in principle, would be the seesaw structure, but that seesaw structure is not observed for transition metals. It's only observed for some main group elements, particular main group elements which are not metals, and those compounds we would typically not view as coordination compounds. So an example is the SF4 that makes this seesaw structure. So the seesaw structure, if you remember this from your first year, is derived from an octahedral structure. So if you add these 2 electron lone pairs to the structure, then we would have overall an octahedron, whereby the corners would be occupied by 4 fluorines and 2 electron lone pairs. And these electron lone pairs are in the SF4 in adjacent position, because the number of 90-degree interactions between the 2 more bulky electron lone pairs are minimized. Okay. So this is the explanation why they actually go in adjacent position and not in opposite transposition. And that results in this typical seesaw structure. Okay, then let's go from the coordination number 4 to the coordination number 5. So this is a coordination number in which we do not have a dominant shape. There are actually two shapes that are about equally common. The first shape is the trigonal bipyramid, and the second shape is the square pyramid. The trigonal bipyramid is slightly more often observed than the square pyramid, but slightly only. Overall, the energies associated with the two structures are fairly similar and approximately equally common. So the pentagonal plane is not known for obvious reasons. If you arrange the ligands in a pentagonal fashion within a plane, then of course they would come far closer together, which is energetically far less favorable. So the coordination of 5 also has another new feature. So in the previous examples, the ligands were all symmetrically equivalent, while in these shapes this is not so. So in the trigonal bipyramid, we distinguish between the equatorial ligands here, 3, and the axial ligands, 2 in this example. And in the case of the square pyramid, we distinguish between the ligands that basically make the square planar base of the pyramid and the remaining ligand, which builds the top corner of the pyramid. So these structures are often fluxional and they can interconvert each other. So you can actually bring in a trigonal bipyramid the ligands that are in the axial position easily into equatorial positions and vice versa, with a mechanism which is called the baric pseudo rotation, in which the square pyramid occurs as an intermediate. And this works the following way. You can see here an example of a trigonal bipyramidal structure. And of course, our molecule vibrates due to the presence of temperature. So statistically, two axial ligands can move so that the 100-degree bond angle is actually decreased. So two ligands can actually move toward each other. At the same time, two of the equatorial ligands, they can basically bend away from each other. So that leads then to a square pyramidal intermediate, which is actually shown here. And if you widen the angle further, then eventually this 120, this angle here, which was originally a 120-degree angle, will become a 180-degree angle, as shown over here. And then these two ligands, which were formerly in equatorial position, are now in an axial position and have a 180-degree angle in between each other. And these two ligands, which were formerly the axial ligands, are now equatorial ligands with a 120-degree angle in between each other. Okay? So you see the entire mechanism here in this animation. You see that these two ligands here, these two, permanently move from equatorial to axial, back to equatorial, to axial, equatorial, to axial, yeah? And these two here, they do the same. So now here, it's the equatorial, now they're axial, now they're back equatorial, they're axial. Okay? You can easily see that this back and forth transformation goes through such a square pyramidal intermediate. Yeah? So for that reason, these structures are often fluxional And when you, for instance, take an NMR spectrum, then it's often not possible to distinguish between ligands in the axial positions and the equatorial position, because that exchange happens faster than the NMR timescale. However, it's possible to slow that process down. For instance, if you take your NMR spectrum at a lower temperature, then that ligand exchange becomes slower and slower and slower, and you will eventually be able to resolve the axial and equatorial position. Or you use just ligands which are extremely bulky, and that also slows down that by pseudo rotation, and you can observe separately equatorial and axial positions. All right, so let's go from the coordination number 5 to the coordination number 6. I previously said that the coordination number 6 is the most common coordination number. It exists for pretty much all electron configuration between B0 and B10 for all kinds of transition metal ions. And the shape which is most common for the coordination number 6 is the octahedral shape, and that is easily understandable because in the octahedral shape the ligands adopt the great distance from each other. They have the smallest steric repulsion. An example is this complex which we already previously encountered, which is the hexacyanoferrate 3. So now there are variations of the theme. You can distort octahedral complexes in a number of ways. So one common way to distort it is the so-called tetragonal distortion. And in this tetragonal distortion, we either elongate along 2 opposite corners or you compress along 2 opposite vertices. So this animation here shows the elongation. Yeah. So we elongate along 2 opposite ligands. Okay, and over here we actually compress along 2 opposite ligands. We're getting a so-called compressed octahedron. So this distortion actually lowers the symmetry. So you know that an undistorted octahedron belongs to the high symmetry point group OH. Can you see what is the symmetry of a tetragonally distorted octahedron? In fact, it's our symmetry again. So virtual students are invited to make suggestions. So the point group is D4H. Yeah. So we certainly retain our C4 principal axis, but in the ideal octahedron we have 3 of those. Now that's reduced to 1, and we have a horizontal mirror plane perpendicular to that C4 axis. Okay, and we also have, well, the 4 C2 axes that stand perpendicular to the C4 axis, and that results in the a dihedral point group type. So it's D4H. So in both the elongated as well as the compressed octahedron, all the faces are being equal, but the ligands have different distances from the central atom. So two ligands have either a longer distance than the other four or shorter distance than the other. Okay, so there's another way to distort an octahedron, and that's the so-called trigonal distortion. So in this case, you do not elongate or compress along two opposite corners, but you actually elongate or compress along two opposite faces. Okay, and the resulting polyhedron is then a so-called trigonal antiprism. It's called antiprism because the two opposite faces here in red, they are twisted relative to each other by 60 degrees. So we can again think about the point group here. So in this case, we would have threefold principal axis that would still go to these two opposite faces. Okay, we would in this case not have a horizontal mirror plane, yeah, but we would still have vertical mirror planes, okay, which would bisect these triangles. Okay, in addition to that, we also still have three C2 axes that stand perpendicular to the principal axis, and that gives it again a dihedral symmetry, and the point group is D3D. Okay, so in this case, are all the faces equal? The answer is no. So certainly these two triangular faces here are different than the remaining ones, the black ones here, which are actually distorted from the ideal triangular shape. But all the metal ligand distances are equal in this case. So each corner here has actually the same distance from the center. All right, so there's another shape that we should discuss, which is not derived from an octahedron, that's the trigonal prism. So the trigonal prism is related to the trigonal antiprism that we just discussed, in the sense that now the two opposite triangular faces are not oriented in a staggered fashion, but in an eclipsed fashion. So this shape is not as ideal as the octahedral shape because it brings the ligands closer together, but sometimes the shape of the ligand enforces the trigonal prism, in particular when we have three bidentate ligands at the top and the bottom of the triangular faces. So bringing the donor atoms closer together, in this case, can actually reduce the ring strain within the ring between the key ligand and the metal. So in this case, what is the pointer? That is the last task for you for today. Any suggestions? Okay, so what is the principal axis? Yeah, so it's a C3 principal axis that goes through the center of these opposite triangles. Okay, so that's always the first question to ask, what's the principal axis? And then you can ask, well, is there a horizontal mirror plane, for instance? And the answer is yes. Yeah. And so then we can still ask, is this a dihedral symmetry or not? And if it's a dihedral symmetry, then there would have to be three C2 axes that stand perpendicular to the C3, and that's the case. So in this case, the first one actually goes through the center of this edge. The second one actually goes through the center of that edge, and the third one goes through the center of that edge. Okay, so for that reason, the symmetry is D3H. Okay, so you can also see that we call this kind of point group the prismatic group. So whenever you see something prismatic, it has to be a prismatic point group which has the edges of the type D and H. So that's another way to derive that. So these trigonal prisms can also be elongated or compressed, but in this case, this doesn't change. All right, then let's stop at that point.